Equilibrium constant, we're looking at the first set of calculations. This one is particularly easy because it's direct substitution. It's not really a long process to get to the value of the constant in this case because it is given, right? So they give us the reaction and it says we've got S, or sulfur plus oxygen gives me sulfur dioxide, and the sulfur is in a solid phase, this is in gas phase, this is also in gas phase. Write an equation for the equilibrium constant. So we've already seen some practice, and this has been a fairly simple one. We say that Kc is equal to the concentration of whatever's on the product side, and in this case it's SO2 raised to the power of 1 because it's balanced, okay, divided by S raised to the power of 1 multiplied by oxygen raised to the power of 1 as well. Now this one's fairly trivial. Now something I didn't tell you in the previous slide, we've done that now, is that solids and liquids, pure solids and liquids, they have an equilibrium constant, or rather a concentration have a concentration at equilibrium of 1. In other words, they don't affect the Kc value of 1. Okay, so that means that this thing over here, the sulfur, its value when I substitute in this whole thing is going to be 1. So that answers question 1. Question 2 takes it further and it says calculate the equilibrium concentration of O2 if Kc equals 6 and the concentration of sulfur dioxide is 3 mol per decimeter cube at equilibrium. Assume that the reaction takes place in a 1 cubic decimeter container. Okay, so that just means I'm going to substitute in the values over here using this pure solids and liquids. I know that's going to be 1. So, and I know Kc is going to have a value of 6. So I'm going to put the value of 6 in over there. I'm going to put in the value of SO2, which is going to be 3 mol per decimeter cubed. And I'm going to put down the value of sulfur over there, that's going to be 1. And this thing over here is going to be what we want to calculate. Now with a little bit of algebra, it's just simple manipulation. That's going to go to this side, and that's going to give me O2 concentration. Sorry, this should actually be square brackets over here, because I haven't really substituted in yet up until this point. And that's going to give me, with some manipulation, that O2 is equal to 3, and that's just obviously 1 times O2 divided by 6, which is going to give me 1 over 2 mol per decimeter cubed. And that's really the equivalent of 0.5 mol per decimeter cubed, right? Just in case your calculator gives you something else. So that was a very simple introductory question. It seemed fairly easy. Okay, direct substitution, always starting with writing out the formula. These are things that we know. Okay.